Hello and welcome and assalamu alaikum everyone. It's an honor that we have Professor Paolo Bottoni with us. He is a full professor at the University of Sapienza of Rome. He has 30 years of experience. He has over 200 publications and has produced more than 50 theses. So he has got amazing track record of, guiding students for masters and PhDs. So, I mean, it's a really good opportunity for us to listen to Professor Paolo and also talk to him, interact with him, and ask him for the opportunities of higher education in Italy. So, without further ado, Professor, over to you.
Hello, does it work?
Yes.
Yep, I think so. Thank you very much for the kind introduction. So now you have built a lot of expectations, so I'm going to disappoint you for sure. But yes, I've been working in a computer science department in Rome for almost 30 years before I was in Milan. But recently I've come to do some research on blockchain and smart contracts. So this is actually joint work with colleagues from the Sapienza University and with a colleague in Milan, an old friend of mine. So those first three names are more on the logical side, whereas with Remo Pereschi from University of Molise, who is again an old friend of mine, and we have established research connections now on this topic. So it is more on the applied side of this. I will talk a bit on the applied side in the seminar tomorrow. But I will anyway start with a presentation of our view of, with some basics about blockchains and smart contracts, which make them available to the formal treatment, which is the second part, the rest of the talk. So this is constructed as a collection of modules on, okay, so how does it, because I have to click, I don't know. So this is thought as a collection of modules, and so that we can also interrupt somehow. And of course, whenever some question arises, please just do it. Let's see if it does it? If I do like this, yeah. Nope. I have to click on the thing. Okay. So first of all, this view of blockchains. I assume that most of you know about blockchains, but just to set the scene, we can give. Sorry, there is a mistake because, yeah. Sorry, just let me correct that because that's bad. Of course, one looks at the slides several times, but this is a substitute gone bad. So, transactions, and this is transactions again. Sorry about that. Okay, let's go back. Okay, let's start again. No, yeah. So this is a view of blockchain. Of course, blockchain is a shared, distributed, immutable ledger recording transactions in a network, and mostly a business network. So what is relevant is that it's shared. So that means that each participant has equal access to the information stored in the network. So now there is possibly a distinction to be made between permissionless blockchains, where everybody can be a node in the blockchain, provided it has the correct software and hardware. Permissioned blockchains, where only those who have received an invitation or have gone through some procedures can participate, and consortium blockchains, which build over some existing or ad hoc consortium, so participation is restricted to those which are there. And this is mostly the thing that we are looking at, these consortium blockchains, which is also the basis for something that I will talk about. But in principle, if you are a node in the blockchain, you have access to all the information in a blockchain, which causes some question whether you want to have your smart contract running on a permissionless blockchain, because then you probably want to restrict access to that kind of information. So you have to encrypt it in some way so that only those who are part of the contract look at that. And this might also have consequences. Sorry, I shouldn't go there. Distributed, well, this is the most important thing. The information is not stored in a central database, but replicated at each node, so that each node, there is a consensus forming in the blockchain on the, on the content of the information which is stored there. Immutable, and this is also essential, an essential property. So once something is put on the blockchain, it cannot be erased, it cannot be modified, lest the whole blockchain has to be forked or something like it happened with Ethereum a few years ago. And this immutability is also an essential part of the kind of logics that will be discussed later. Well, ledger, it's means that business information is stored. So in principle, once we know that it is there, we can also abstract from the mechanism by which information is put in the blockchain, whether it is by proof of work or by proof of stake, and just to think of it as being there. Transactions, this is the other important thing, is that means that we are mostly interested in the fact that some asset, which can be a digital asset or can be the digital twin of a physical asset. If I sell my car, then it's recorded somewhere, but I gave it to somebody. And this means that we will model what's going on in a blockchain as a collection of transactions, saying that this asset was with Paolo Bottoni at a certain point, at a certain moment, and after this moment is with Remo Pareschi. And finally, they are on a network, so there is a collection of global interconnected nodes and mostly a peer-to-peer architecture, so that the transactions can go on. So does it go like this? Yeah. Yeah. So one of the things that the the transaction allows you to, in the sense of smart contracts, is that in the traditional view, when you sell your car, or when you buy your car and then you dispose of it, so the whole life cycle of a car, means that there is a series of ledgers, databases, which tell you at each moment where the car is. So at the beginning, the car is with the manufacturer, then it's transferred to the dealer, then it's gone to a leasing company, for example, then it's gone to a lessor, and then finally it is disposed of to a scrap merchant. So every actor in this line, in this life cycle, has its own ledger, has its own local view of the information. And there is a regulator which maintains the global view of this by collecting information. So this could be the Office of Motorization in Italy, for example. So they need to know that a car with a certain identifier has gone through all of these topics. But whereas for each individual actor, it's not relevant what will happen in the future or what is the story so far. With a blockchain, instead, each actor is seen as a node in the network, and all the information is maintained in the network for the whole life cycle of a car, which means that every actor can know what is the story so far and can put its contribution. So it has entered and it has gone out. And the regulator is a node itself, and so it has access at each moment to the whole information. So this also creates the possibility of developing smart contracts on this, because, for example, you might have regulations so some transaction can be legal under certain conditions, and for example, you cannot lease the same thing twice at the same time. So the structure of a blockchain, as the name says, is a chain of blocks. And as we know, each block has its own hash. So there is almost unique, but the possibility that you have a conflict of hash is infinitesimal. Encryption, identification of the content of that particular block. And each block can contain a number of transactions. For example, block 1575 has one transaction in it, block 1574 has two transactions in it. And transactions are time-stamped, and they identify the transfer of this digital asset. Or of a digital twin of a physical one. So we take this atomic view of individual transactions, and a block can contain a set of such individual transactions. We're not particularly interested here in how they are added to a block, but a block uniquely collects a set of transactions again. I made a change all, but I didn't notice that it had this effect. So it uniquely collects a set of transactions. So why is that immutable? Because of a hash mechanism. So the hash is built by considering the hash which is calculated on the transactions in this block and the hash associated with the previous block. So if you add a block, then you need to uniquely connect it to the previous block. And then you can check that the hash for this block is consistent with the fact that the previous block will add that hash. So actually, you have the header of the block where you have some information. So you have the hash of the previous block, and you have the markable root, which is a representation of a tree which forms the whole blockchain. The timestamp, the bits is the target. So you must build your hash consistently with that kind of information, and the nonce is a number that you have to add in order to create a unique hash. So the important thing here is that there might be conflicts on whether you can connect a block to the previous ones. And this is where consensus comes in. So, for example, there is always a genesis block, so-called. It's the one, the leftmost one. And things have started by adding one block. And now there are, since it is a node, it is a network, so a set of nodes says, this is the block that I'm going to add, because I want to add this set of transactions, and another set of nodes says, no, now we are going to add this other set of transactions. And so consensus is reached by majority, and majority can be in different things. So the block which doesn't reach a majority is the one in purple now, and it stays there. How do we decide which is the correct one? By the fact that the next ones will attach to the black one, and nobody will attach to the orphan one. So it will remain there. It is not deleted. It will remain there, but nobody will ever look at it. And this can happen at different times. So you see that you have situations where another block is attached to something which will ultimately become an orphan, because you always look at the longest possible chain. So once the rightmost block has been added to the one on the top, then it becomes the longest chain. So the other ones are removed from there. Okay. Well, are ignored in the rest. So this is what is the basis for the discussion. So smart contracts, in principle, very independent of the fact of being put on a blockchain, but it's a convenient way to put them on a blockchain is a convenient way to have some trusted information on the smart contract, on the current situation of a contract. So assume that a contract says under which conditions some transactions can be done. And so everybody can look at the conditions were verified when a transaction occurred. And if it is on a blockchain, then you don't need a central authority, you don't need a trusted database for this, which might be relevant if the smart contracts, for example, cover actors which are in different continents, for example. So a digital agreement or set of rules that govern a transaction or a sequence thereof. And mostly we are interested in contracts which have a duration, so they can involve a number of transactions. And it's basically a program. Okay. So steps are activated when a transaction is performed or when some event occurs. So smart contracts were first put on a blockchain with Ethereum, because Ethereum provided a language, solidity for writing contracts, and they become they can produce transactions on the blockchain. So you put the contract on the blockchain so that it's visible by every participant, and then it's activated when it's needed. So a transaction in Solidity is a message that is sent from one account to another account, which might be the same account or an empty one. And it can include binary data, which is the so-called payload, so where the information really is there, and ether or gas, so the currency that runs on Ethereum. So you basically have to pay for recording your transaction, and you also might say that I transfer this amount of gas or ether to this other guy. The target count, if a target count contains code, that code is executed and the payload is provided as input data. So that's what happens in Solidity. Now, there are other kind of blockchains, and in particular the ones based on Hyperledger, which is mostly oriented towards permissioned blockchains, which do not use a specific language, but for example, Hyperledger uses Fabric, which is a framework where you can write smart contracts with, in different languages and be transformed, so to speak, into this kind of transaction. So in Solidity, for example, you have this kind of contract owned token. So this represents the fact that a token, which might be a representative of some asset, is owned at any moment by somebody. It is created by a token creator. It stays with the owner, which is address. It's a type, data type in Solidity. It has a name which is encoded in bytes 32, and there is a constructor which says, well, this token is owned by the sender of a message, and it has been created by this token creator. Then we can change the name of a token. And most importantly, we can transfer the token to a new owner. We only accept this transfer if the sender of a message which says that transfer is the owner. So nobody can say transfer this token from A to B, but only A can send the message transfer it to B. And then we actually have to ask the creator if it is okay to transfer this token, because the creator might have set some condition on it. So if this check is okay, then we do the transferring. And the token creator is like this. So it's the one which returns the token address of the own token with a name. It can change the name, and it has this condition for transferring the token. So when we ask if it is okay to transfer the token, it will return a value based on some arbitrary condition which is represented there, for example. Okay. So this is a very simple contract. So how do we relate to things which happen in the real world? And again, in Ethereum, this is done with oracles. So this represents a way to bring data from off-chain data sources into the blockchain for smart contracts to use. Because the blockchain can only refer to things that are known to the blockchain. So imagine a situation where you have bets online, and they're recorded on the blockchain, but at a certain point you want to know who won between Liverpool and Arsenal, because the payment is based on that result. And this is not some information which can be arbitrarily put in the blockchain. So we have to resort to an oracle, which is some official documentation of a result. And the oracle will inject its response. So the oracle must have some API for introducing, must access some API to get the data and introduce it in the blockchain. Another case could be if a contract has some force majeure clause. So for example, you said, I give 1 ton of corn from my crop by that day, but I put a force majeure clause. If conditions of weather were bad, then I will give you half a ton. And how do we know if the conditions of weather were bad? So we need to identify an official authority which will tell us about the weather conditions and interrogate it with the oracle and introduce the response. So the oracle must be a trusted one again. What we are working on, and it will be the topic of tomorrow's talk actually, is the introduction of supply chains into the blockchain as smart contracts. So the idea is that you will have an originator which will produce a contract which says, I need this part, and this part in order to create the final product. And the suppliers will say, I will provide this at this price, I will provide this amount of this at this price. And of course, suppliers can rely on suppliers of raw material or semi-processed material, and it's a chain. So they will produce it, they will transport, the product will be sold. Typically, it could be sold by the originator, or the supply chain can have some merchant in it, which takes the load of selling the product. And every transaction will be recorded on the blockchain, and the smart contract will be recorded on the blockchain, so that everybody can know what's happening with the supply chain to which they are participating. So this is where we are interested mostly. This is the kind of implementation that we did, but I'm not going into the details of this. But this is based on Ethereum. The interesting thing is that, for example, we recur to a store of information via IPFS, where we can deposit, for example, the documentation. So if each transaction comes with a PDF file which says what has been transferred to, we record this a digital twin of this transaction, but then we want to look at the physical document. We don't want to put the physical document on the blockchain because it will cost a lot, because it's a lot of bits. So we put it on an external storage, but with some guarantee of immutability again. And we record the identifier of a storage on the blockchain. So everybody can go back from that identifier to look at the actual document. So this is the perspective we are moving in. Any questions so far? Okay, so I'm going to present our view of contracts, of configurations of ownership of the tokens, and the representation of transactions, which creates the formal basis for the discussion. So we are not going into the details of mining, of proof by stake, proof. We are just looking at the fact that there is a contract which says something will be moved from here to here if this condition is valid. So we wanted to identify a model for contracts amenable to formal analysis and with good properties for logics. So the kind of logics that we are going to use is fundamentally a temporal logics, which says something will be true up to a point, or something will be true from a certain point onwards, or if this becomes true at a certain point, this other thing will become true later, this kind of things. But we also are interested in modal logic. So is it possible that this is true? Is it possible that this will become true? So, of course, we are interested in contracts because we are dealing with smart contracts. But the interesting thing is that smart contracts can be the translation of a legal contract. Okay, so what you have is a legal contract which is written in natural language. And so you want to say this part of the contract means exactly this. And from the computational point of view, this means that this will happen in this way and this other way. So this is important because we can then verify the execution. Is it possible to do this transaction? Or even, was it legal to do this transaction at that point? Because the point is that once the contract is transformed into a program, if you look at the program, it's very hard to verify. It's written in some language. It's written in some language which might not have all the formal properties for verification. So maybe it involves pointers, for example. So how can you be sure that your implementation is the correct one for that contract? You had two problems. How can you ensure that your interpretation as a program is the correct interpretation for the legal aspect of a contract? And how can you be sure that it has been implemented correctly? So we take a very abstract view of contracts. So a contract defines a partial order on a set of transactions. Partial order means that you cannot do this transaction if you have not done this our transaction or this collection of transactions before. But not all transactions are related to all transactions. Okay? And a transaction is, we take a very simple view, but it's consistent with what we saw, for example, in the solidity example. A transaction modifies allocations of resources to actor. So a transaction says this asset went from A to B. There is one thing that has to be said, that the whole construction that we are going to look at now is based on a finite model of contracts. So we are not dealing with contracts which say whenever A gives $100 to B, then C will give $100 to B. So, for example, you can have these schemes. If you donate this society will donate the equivalent. So this can happen, but it has to be finite. So this will be true up to midnight of the 31st December, and the donation will be up to $1 million. This is essential so that we can reason on the fact that you can have only a finite set of a finite number of transactions which can occur. It can be adapted to an infinite view, but it would require some technicality. And actually, contracts are finite in this sense. So they involve a finite set of actors on a finite set of resources. It is possible that not all the actors are known in advance. It is possible that not all the resources are known in advance, but we know that we cannot have more than 1,000 participants, more than 1 million transactions so far. So we avoid the perpetual concessions, but we might have concessions from here to 2099, 999, for example. Then it's still finite. So a smart contract here is a template with parameterized definitions. We take examples from Cicero, and the definition can be associated with computation. So this is an example. This is a smart contract for acceptance of a delivery. So there is a shipper which has to deliver some good and give it to a receiver, and the good is the deliverable. So shipper will be deemed to have completed its delivery obligations if, in receiver's opinion, the deliverable satisfies the acceptance criteria and the receiver notifies the shipper in writing that it is accepted the delivery. So all this highlighted part, there is some syntax there, which says you had to take this parameter shipper, and for any specific contract, the shipper will be UPS, DHL, whatever, and the receiver is the one who has made the buy, and the deliverable is this piece of equipment that I bought on Amazon, and so on and so forth. So here it's quite simple. There are just parameters which are filled with information which is taken from the actual contract. But there is some computation because you need to retrieve the thing. So this is a template for a smart contract, and all the contracts will be written according to this. So you can find this in the where is the, no. You find this in the web page for Cicero, which is the language defined by this Accord project to write smart contracts. Again, inspection and notice. The receiver will have a certain number of business days to inspect and evaluate the deliverable on the delivery date before notifying the shipper that is either accepting or rejecting the delivery. So here there is some computations involved because you have to check the day in which the deliverable has been delivered with the day of the notification, and you have to compare it with this with this parameter here. And finally, the acceptance criteria are the specifications of the deliverable that the deliverable must meet for the shipper to comply, etc., etc. So this is the kind of thing that we are looking at when we speak of smart contract. So as you see, that is independent of the language in which it will be realized. And the ACOR project is so that you can automatically generate programs based on this template. So what we want to do is to model a contract as a sequence of sets of atomic transformations applied transaction. So this is the most important thing. So we are not looking at individual transactions only, but we are saying that some transaction must be co-occurrent. So you progress, you make the contract progress if both A has given something to B and C has given something to D. After that, then you can progress. As we said, transactions are seen as transformations or locations of resources to token. This was the owner before, and this is the owner after. So we can model things like this. There is a delivery obligation. So the contract starts with a delivery obligation, which is given to the shipper. And this top sign here means that before the delivery obligation is created for the shipper, it was not existing, but we knew that it should have been, that it will be produced. So this top means this kind of this resource is not with a proper owner yet. It will be, but for the moment is there to be waiting to be given to a proper owner. So we start with obligating the shipper to deliver, and we start with giving the deliverable to the shipper. And once again, before the deliverable is given to the shipper, it's not part of the contract. Of course, the correspondent piece of good is there, but it's not part of the contract yet, because they were only interested in the shipping thing. Now, there are two things which which have to happen concurrently. Concurrently doesn't really mean at the same time, but here it means that no matter the order in which they are produced, they must be both. They must both happen before we can go on. So we will the shipper will give a deliverable to the receiver, and an acceptance notification will also have to be given to the receiver to prepare and complete. Now, the acceptance notification can be given from the receiver to the shipper. Typically, it will have changed its state, but we're not dealing with that at this moment. So at that point, we say that the delivery obligation of the shipper has been completed, and so we discharge it. And again, this bottom symbol represents the fact that that resource is no longer available for transaction. So once the delivery obligation is discharged, the shipper has nothing to do with it, and nobody can say, well, I got this delivery obligation, why didn't you give it? And finally, we have the fact that the shipper now has something which testifies that the deliverable has been given, that the delivery is complete. Because otherwise, it would not have a delivery obligation anymore, but there is no proof that it has shipped. Okay? So this is what has to happen. And at any point, the hour allocations, which are not modified by this set of transactions are left untouched. So after T1, the delivery obligation is still with the shipper. After T2, the delivery obligation is still with the shipper. And after T3, the deliverable is still with the receiver. So if we want to have if we want to go to the model for all of this to be expressed, we have a finite set of resources and a finite set of actors. And the actors include these top and bottom symbols, okay, that can be used only for that. So that means that you cannot you cannot have any transaction which starts from the bottom. Okay. So there are admissible allocations. So it's a relation between resources and actors, which means that not all resources can be given to all actors. So for example, the receiver will not have any delivery obligation. And then there is an assignment function of resources to actors. And assignment functions must be consistent with a relation which describes the admissible allocation. So the transactions must be consistent. Resources are atomic. There is some way to deal with non-atomic resources, so divisible resources, quantity of water, but for this account, we consider them as atomic. And there are atomic transactions, so they are represented like this. A resource was with actor K1 and now is with actor K2, the same resource. K1 must be different from K2, of course, and K1 must be different from the bottom. So once something is at the bottom, you cannot use it anymore in a transaction. You can also model events, which are a subset of special kind of resources. The point is that events can only be allocated to bottom and to top. So the only thing that can happen is that a certain event was waiting to occur and now it has occurred. And once it has occurred, it cannot occur anymore. Okay. And any event is of this type. Okay. So this allows us to model the fact that things happen and can be recorded as part of a contract. So now a transaction represents a change in the assignment. So you have a function which defines what is the allocation of resources to actors at any given moment, and you change the function. Okay? And you want that property that we discussed, that if allocation is not involved in a transaction, it remains there. And the other thing is that if you have a set of atomic transactions in a transaction, this must succeed or fail as a whole. So the success makes the new assignment persistent, whereas the failure restores the previous one. So you have acid properties of database, mostly. So what we can do is to model things like this. So you have a universe of allocations, and you have actions, atomic transactions, that, as we discussed, we say as the transfer of a resource from an actor to a different one. You can say which is the I don't remember why I called this name. So the actor which creates the the actions and the actor which receives the action, and the resource which is involved in the exchange. And what is the originating actor? What is the target actor? And you have this function for this action. You have the way in which it modifies the allocation. So it is quite simple. So if RQA is in the current assignment, then you can apply this. So you're saying that you're saying that I can do this only if K1 is the current owner of R. So the allocation of R to K1 is in the current state of a contract. If this is the case, then you remove the original allocation and you put the new allocation. Okay? And as you see, all the other ones are left untouched. They vary. In L1, you modify only this one. Okay? So yeah, RQ means required, and GT means guaranteed. So before, it is required that R is given to K1, and after the transaction is guaranteed that R is given to K2. If this fails, so if K1 was not the owner of R, you request him to do this transaction, but it's not possible at this time, so you just stay there. But if a transaction succeeds, then you're guaranteed that the configuration is a different one. And if we want to take a set of transactions, then we together, then we say that this constitutes a kernel, the kernel of a global transaction. So one condition is that the resources which are involved in all these atomic transactions are different. So we are saying that it's not possible at the same time that A gives R to B and B gives R to C. We must consolidate the fact that R is with B before it is possible that B gives it to C. So now we can redefine a new function to modify assignments as the combined effect of all the transactions which are there. So you remove the current situation for each assignment which is required in the kernel, and you add the guaranteed part. So you remove the required part and you add the guaranteed part for each assignment that is in the kernel. But it is this is possible only if all of the required parts were in the current assignment. So if one of these fails, then we restore. Resources cannot disappear, and a transition is completely determined by this kernel. Okay. Other questions? So this is the essence of all that comes later. So now, what is a contract? A contract is a set, is a triple with S over rho. This is the encoding of a set of admissible allocations. So we have a relation rho, and we say all of these allocations are possible. TA is an encoding of a set of atomic transactions, and TRNS is a set of admissible transactions. Now we can give names to the transactions, but transactions, now I mean the set of atomic transactions that we want to use. So there are a number of transactions which we say these must occur concurrently. And we have an alphabet for the whole thing, for the system of transaction, which says which are the admissible allocations and which are the names of a transaction. So this is a system of transactions for us. Now, a contract is based on this system of transaction, U over tau. An authorization function, an initial set of possible configurations, a set of configurations which are said to honor the contract, so everything went according to the contract, and a set of configurations which represent breaches of a contract. So at some time, somebody did not fulfill their obligations. So all of these these three sets must be subsets of sets of admissible allocations. And the offering function relates a set of admissible allocations to a set of admissible transactions. So if this is the current state, then you can apply this set of transactions on it. What we require is that if you have an initial state of a contract, then you must be able to authorize something, because otherwise the contract will not start. And when you have a finite, you have a configuration which belongs in the possible final configuration, so those where the contract is honored or there has been a breach, then you cannot go on with the contract. So it's finished. For breaches, you can do something different when we will see. So this is the definition, but then you have executions. So executions means that you apply transactions in sequence, but you say that this is an execution of a contract if the sequence is consistent with the authorization function. So basically what you will have is a sequence of configurations, L0, Lk. L0 is in the initial, is a possible initial one, and Lk is a possible final one. And at each step, we apply the progress function on the current configuration using a kernel which must be authorized for that configuration. So you have a kernel. It must be in the set of transactions which authorize on Li. Then you can apply the kernel to Li, and we assume it succeeds because, of course, you must have the authorization function defined in a way that it succeeds, and then you have a new configuration. There is one thing to be said here. I'm speaking of succeeding, but succeeding means that it can also lead to a breach. So we are not saying that only the honored, the path which go to honored are successful, but because things might happen which lead to a breach, and you must be able to capture this. So you must also model transactions which lead to a breach. And we will see examples later. So this is the example that we saw before. So at the beginning, you have that all the resources which we mentioned are at the top. They're not being made available yet. And in the end, we want to finish with a situation where the delivery obligation has been discharged, the deliverable is with the receiver, and the certification of deliverable, delivery complete, and acceptance notification are with the shipper. What are the breach configurations? So here is here is the first situation is the delivery obligation has been discharged, the shipper has the delivery complete, the document, and the acceptance notification. but actually the deliverable is still with the shipper. So somehow they forged their discharge documents, but they didn't give the deliverable. And the other one is the opposite. So the delivery obligation is still with the shipper, but the delivery has been completed, the deliverable is with the receiver, but the acceptance notification has not been given. So the receiver has kept the good, but has not discharged really the shipper. So these are the transactions which model that. So in a situation where you were waiting for T2 to happen, T2 prime happens. So we give a receiver and then we don't proceed. Or in a situation where we are waiting for T3 to happen, we don't give the acceptance notification. So you had to model this as well. Okay. So this is a situation where we said the delivery obligation will be given to the shipper, the delivery completion will be given to the shipper, but the activity notification will be given to the shipper. And this is where only the deliverable has been given to the receiver, but the receiver has not done anything. So this is the authorization control function. At the beginning, we can only do T0. Then things have to progress. In the situation which is consequent to T0, T1 must happen. But in the situation which is consistent with the fact that the deliverable is with the shipper and the acceptance notification is not being given to anybody, then the two things can happen. T2, tau 2 prime, tau 2 seconds. So these two things can also happen. And finally, when things are consistent, then we can perform the final one. So this is for a successful execution. So where a successful one is one which leads to honoring the contract. This is what will happen. So we first give the delivery obligation to the shipper, then we proceed and we give a deliverable to the shipper, and we then give deliverable to the receiver, and the acceptance notification is with the receiver, and then delivery obligation is discharged, the deliverable is the receiver, the shipper has the acceptance notification, and the information that the deliverable has been completed. If something goes wrong, so from the situation that you reached with T1, our T2 prime or T2 second will occur, and we will end with a breach. So this is just an animation of how things go. So in this basket, you see things that are still on the top. Now the delivery obligation is with the shipper. Now the deliverable has been removed from the basket and given to the shipper. Now the shipper gives the deliverable to the receiver, which is ready with a acceptance notification. You see the basket is empty. The shipper has the delivery complete and the acceptance notification. The receiver has the deliverable, and the delivery obligation has been discharged, and it's in the basket. So one last thing is that if a contract is very complex, you can have many transactions, and you might want to have some strategy of execution, because They might involve some cost and so on. So you can do two different things based on the fact, based on the property that all of the resources in a transaction, in a kernel, are different. You can have a parallel decomposition, or you can have a parallel composition. So in a parallel decomposition, you say, okay, I have this 100 atomic transactions that have to occur concurrently, but let's say that the first 50 will occur first and the second 50 will occur next. So you create two transactions out of this. And the opposite is for the merging. So you have if you have two kernels with all different resources, then you can merge to a single one. So I have these 30 resources in this set of transactions, and these other 40 resources in this other kernel. They're all different, so that I can merge them into a kernel of 70 transactions. And the other thing that you can do is a sequential composition. So once again, if you have said that this must occur before and this must occur after, but once again, you know that if you have done T1, you will immediately do T2 because after T1, the only thing that is authorized is T2. And the resources in the kernel of T2 are different from the resources of the kernel of T1. Sorry, if you have the same resource, but in T2, in T1 goes from K1 to K2, and in T2 goes from K2 to K3, then you can say, well, let's give it to K3 immediately. Okay, you don't wait for other things to occur. So you compose them by cutting a step, basically. So this means that you can look at this situation. So you have T1 and T2, Tau1 and Tau2, which can occur in any order because they're all independent. And so if you go from, you first apply Ti1, you reach L1, you then apply Tau2, you reach L prime, or you first apply Tau2 and you reach L2, and then apply Tau1 and you reach the same L prime. Then it means that you can parallel, you can do things in parallel. And the thing is that if any of them fails, then their composition will fail. If both of them succeed, then their composition will succeed. Whereas for this situation here, so it's this is the case where both fail. For Tau1 or Tau2, they both fail. This is the situation where, let's say that Tau1 fails on L, so it remains L. So the parallel composition will fail on L, and it will remain in L. And then maybe Tau2 will succeed in L, and so you reach L2. And the opposite is here. Tau2 succeeds on L, and you're guaranteed that if it succeeds on L here, it succeeds on L here because it's the same L. But you know now that Tau1 will fail, so their composition will fail. So in any case, you will reach L2, but one of them will have failed, which is not very much desirable, of course, but it's what can happen. For sequential composition, then you have different situations because you might, let's say that we do a maximal composition, so everything that can be composed will be. So that means you have said that tau 1 contains 30 transfers, tau 2 contains 50 transfers, but 20 of them are consecutive. So you can compose them in sequential composition. And that basically means that this part is independent of the others. So now you have 3 sets of resources. Those which are directly transferred to the final destination, those who are transferred with T1 but not with tau 2, and those which are transferred with tau 2 but not with T1. So the composition of tau 1 or tau 2 can happen at any time. You can happen on the original set or on the set that result from this. But you know that you can apply parallel composition to the other one. So these are now independent. So no matter the order, you will reach the same things. Or you can say, well, I will apply tau 1, then I will apply the sequential composition here, and then I will apply the remaining part of tau 2. Or I will apply the remaining part of tau 2, then the sequential composition, and then the remaining part of tau 1. And I will get the same result. So these are properties that are maintained. So once you implement, once you have defined the basic set kernels, then you can go on and implement as you wish, provided that you respect this method. So to conclude this part, and maybe we can have a pause after that, we model contracts in terms of modifications of resource allocations, and we look at contracts as defined in a special form of nest functions, where this, the state is represented by a set of allocations. The way in which we have modeled this means that we can compose and decompose transactions, giving rise to equivalent contract execution, which is an interesting property for formal verification. So I will stop here for the moment. And then we can go with the rest, which is the basis for the logic treatment. I don't know if we can cover all of this, but for sure I want to talk about automata after the pause. Okay. 10 minutes? Yeah. Okay, thank you.
We take a 10-minute break, and then how long is your second part of the lecture? How long is the second part of the lecture?
It's more or less equivalent, but as I said, it's modular. So, for example, I can skip the last part. So. I thought it should last until 1 o'clock, but it doesn't matter. So, of course, if there are questions, meanwhile, I'll be happy to entertain them. Otherwise,
Any questions so far?
Yep.
So why is the formal notation so important to model those transactions?
Why do I need the locations?
Yeah, the formal notation, all the sets and the operation, all the sets and the operations. Why is that so important?
Was actually where are they stored? You mean? Or?
Yeah, but like how people on YouTube, how they teach Solidity and smart contracts, they don't really use formal notation.
No, exactly. That's what we are doing because we want to establish logic. So the whole thing is to be able to say this was possible. Well, I don't want to anticipate too much, but you reach a certain situation and you say, okay, but something went wrong here. Where did it go wrong? And at that point you say, here you took this path, but you could have taken that path instead. Or I reach a point and I say, is this point still a situation where I can honor the contract, or is it irremediably broken? So in order to do this, I need a logic. And in order to have a logic, I need to have some formal thing to yeah. So the idea is that at any state, in any case, you can model the current situation in these terms. Because
I've done a few YouTube courses and certifications on blockchain, but and I was following along, but as soon as you started reaching the formal part of the transactions part, I got lost.
okay.
Thanks, sir.
I will go back. I will go back to.
It will be more application based, you said? Tomorrow the talk will be more application based.
Yeah, tomorrow is in general about IT and growth. I will present some case studies, but I will not go into much technical detail.
So the Accord project and Cicero, that's you're personally involved in that?
No, I just take it as an example.
It's very good.
Yeah, yeah.
Thanks.
So maybe some students going for the break.
Mm-hmm.
Many students have a class,
Okay.
so they may not come back.
I see.
So we can wait for some time and then we can maybe conclude after a short time.
Okay. Need to do the offer to the client within a certain time. The client must accept it. So this is the automaton. So you start with an initial state where you are waiting for some documentation of the damage. And so when the damage has occurred, and you have the documentation, then you are in the active state, and then you need to claim the damage within a certain. You cannot wait 1 month to claim. So if you don't do that, then after 1 month you reach the deadline, and then it's claimed, and you send the documentation. So now the responsibility is with the company; they must send you. If they don't do this within this time, then this is a breach of the contract. This one is not, because you are not required to claim the damage. You don't want to claim it. But this is a breach. Now the offer is made, and again you have a timeout. So if a client doesn't accept, then it's not a breach of the contract, because it is considered that they cannot respond. And if it is rejected, if the client rejects, then you finish in the rejected state, which is a possible final state. Or if they accept, then the insurance company has to do this, refund the risk, and this is a non-risk state. But if they don't do this within the timeout, then it is a breach of the contract. And this is how things can happen. So you see that there are 1, 2, 3 composite transactions where you have 2 atomic transactions which must occur. And transactions to timeout are single, so they're activated when the timeout is. So now there is a way to remodel this in terms of our model, but I'm not going into details. But the fact is that all of the things that are mentioned are transformed as are modeled as resources, including the timeouts. And basically, these resources represent documents which are exchanged within the participants. And once again, these documents can be PDF, or can be actors are the customer and the insurer, and you still need the bottom when you have all of the things that you see before, the downloads. Now we can go to verification. So the point is that the ledger does not record the transactions. So there is nothing in the blockchain mechanism or in the distributed ledger mechanism which says you need to record the claim and send off together in the same block. So maybe you record the claim in one block and the send off comes after 3 blocks. Because the mechanism of recording transaction of the blocks is completely independent. So that's why what we deal with in, when we look at the record of the ledger is a sequence of atomic transfers. And we need to reconstruct whether they were in accordance to the contract. So what we can do is verify of the state of the ledger is consistent with the contract, and if sequences of transfer must produce legal statements. This gives us a tree representation, and since we are close, I will just show you this. So logic for ledgers, and this is the idea. This is the idea that each ledger can be modeled as a tree. So you start with this initial situation where everything is still possible. So remember that we were dealing with finite resources, with finite set of actors. So there is a finite set of possible transactions. So in principle, you can represent each possible evolution of your ledger as this kind of. Every time a transaction is actually registered, then you reduce the possible evolutions. So remember that we look at blocks. So these blocks can include a set of atomic transactions. And some of these are related to your contract, and some are. But let's say that at a certain point you find out that this is a consistent state, and this is a consistent state. And each consistent state that you reach reduces the possible functions. So in the end, you will finish your contract and you will honor and you can construct the same structure for both atomic. So in one case, you just consider the consistent state, and in the other case, you consider all possible. So based on this, through some technical let's say that the battery is running low. So I'm almost finished. So there is a number of things that happen. So the logic is actually constructed in an algebraic way. There is some category theory involved, so I'm not going into detail. But the idea is that it's not connected to the power. But the idea is that these three define possible truth. So something is true if it is on a path on the tree. So a collection of paths defines a set of truths. And then you can say, well, if this was true at this point, this can become true at another point. But this will not become true anymore because it has bifurcated. So we can construct a logic with this, and then we can have a set of operators. So it was there a time that this was true, was there a time that this was still then you can query this kind of thing. I'm sorry that it's dead, but there was, maybe I can use mine just for a moment. I want to show the references of the paper. So if somebody is interested, they can. So these are the relevant references. So the first one is very heavily mathematical stuff. It goes mathematical structure of computer science. And the second one is basically an application of the model from the previous one, but with some sort of simplification. And with application to the blockchain and to this model of application. The other one is independent. It has to do with processes. Then this one is on intelligent smart contracts for innovative supply chain management. Is the example I gave. I will talk a bit more about it tomorrow. And there are other papers on supply chain that I will show the references tomorrow for that. This one on theoretical computer science, is the model of transaction and contracts adapted to reaction systems, which are a particular model proposed by Professor Rosenberg for dealing with finite set rewriting of a particular type, which fits well with the notion of contract that I have defined. And the other one is on the logic part, and this is where we introduced the automaton, and we developed the theory based on this automaton. And this has applied at the end of 2022 in blockchain research and applications, which is a new journal, relatively new journal, dedicated to blockchain. So if anybody is interested, they can look at them, or they can go on DBLP and look at my papers for 4 years. Okay, sorry.
We have got another meeting and the faculty is waiting. So we have to rush. Okay.
Well, it's more